Okay, so very good. Let's move into the topics for today. So last time we were talking about eclipses, and we got partway through the basics with eclipses. Let's get some slides going here. Okay, so we talked about lunar eclipses, where the moon is passing through Earth's shadow. Earth has a big shadow, so it spends about 100 minutes in there. It's easily seen. Everyone on the back side of the planet can see this, the night side of the planet. And we talked about solar eclipses, where the moon's on the other side. And so the moon being small, it casts a small shadow that makes its way down and just barely touches the Earth. As we'll see, sometimes it doesn't touch the Earth, but we consider the cases where it does touch the Earth. And so this is a solar eclipse, and it can be either total. If you're in this cone of totality, you can see here it's coming down and just touching the Earth, a little spot, then you have a total eclipse. Or if you're in this broader region, it could be a partial. And the total is obvious. If you're in the path of totality, it's obvious. Daytime turns to night. But if you're in this larger spot with the partial, most of the time you won't even know it's happening. You can block 50, 60, 70, 80% of the sun, and it's just like a cloud passed overhead. And so you don't really realize it unless you know to look. And we talked about various ways, interesting ways in which you can try to see it. Okay, so one more type of eclipse, and it is a type of partial, but it's also a perfect alignment like a total. So it's kind of its own special case. These are called annular eclipses, referring to annulus, not something that happens annually, but annular refers to annulus, like a ring, because that's how it appears. And it has to do with the fact that the moon's orbit around the sun is not perfectly circular. Here you see the moon, the Earth, and those are not to scale, right? They're drawn too big, and we talked about this. Most of these diagrams are not going to be to scale. But what is to scale in this diagram is the orbit, the shape of the orbit. And if you look at it carefully, it's not perfectly circular. And we'll learn this going into lesson 2, particularly once we get to Kepler, that orbits are not perfectly circular, they're ellipses, where a circle is a special case of an ellipse. And a lot of the orbits, like planets going around the sun, like Earth's orbit going around the sun, is almost perfectly circular. But technically, they're all ellipses. And if you look at this, you can kind of barely see it. This is when the moon is as far away from the Earth as it can get. And over here would be as close as it can get. Let's see, I have a little animation here. I think I have it preloaded. And so this is just pulled off Wikipedia, but this is a picture of the moon taken every day throughout the entire phase cycle. And so you see it going through the phases, but ignore the phases for the time being and just look at the size of the moon. Sometimes, like now, it's getting a little bit bigger and a little bit smaller. And that is just due to, is it close like right now, or is it far away? The farther away something is, the smaller it will appear. It doesn't actually physically get smaller, just its angular size, its apparent size gets smaller, and that's just as it's working its way around the orbit. So you have these two extremes. On the left is the moon at closest approach, and on the right you have the moon when it's as far away as it can be. And as you can see, there's a 12% difference between these. Now, many people come up to me, and this has probably been your experience as well. They say, hey, did you see the moon last night? It was so big. Or it looked really tiny last night. Have you ever had that experience where the moon looked big in particular? You may not have thought about it, but think back. Was the moon on the horizon when it looked big? Low in the sky. I can almost guarantee it was. That effect is not this effect. This effect here is a slow change in the true apparent size of the moon. Over the course of 2 weeks, it gets bigger. In 2 weeks, it gets smaller, slowly each day. And it has nothing to do with whether it was high in the sky or low in the horizon. This is a real effect, but a small effect, and not one that you generally notice. The other effect is a psychological effect, an optical illusion of sorts, a psychological defect, collective defect in all of our minds. And I'll come back to it. I'm going to skip over it right now, make sure I get through all the material you need to answer the questions in homework 1. Then if there's time at the end, I'll come back and demonstrate the psychological effect because it's kind of cool. But yeah, that effect that you've possibly noticed before is just in your mind. The moon doesn't actually get bigger when it's low in the sky and smaller when it's above. Okay, now, so we have two sizes here, and a range of sizes for the moon. The sun is, of course, big, 100 times the size of the Earth. It's really big, but it's far away. And those two things cancel out to give us an object that's about half a degree across. The moon is a lot smaller, at 1/4 the size of the Earth, but it's a lot closer, and those things cancel out to give us an object that's about half a degree across. So coincidentally, the moon and the sun occupy the same angular size in the sky. Now, as you can see here, sometimes the moon is a little bit bigger than half a degree, and sometimes it's a little bit smaller than half a degree. So when the moon is close and bigger, it's bigger from an angular point of view than the sun. And so it can cover up the whole sun and give us a total eclipse. Though on the right here, when it's a little bit farther from Earth, a little bit smaller from an angle point of view, its apparent size is smaller, it's not quite enough to cover up the sun. So even with a perfect alignment, you're still going to get sunlight in a ring, an annulus, going around the moon. So here's the geometry for that. Here's the moon when it's a little bit farther from the sun. If I go back to what we were looking at before, here's the moon when it's a little bit closer. The cone of totality goes down and touches the Earth. But when the moon's a little bit farther in its orbit, the cone of totality stops at this point above the surface of the Earth. And so even if you're perfectly aligned, you still have a partial. I think there's one of these in the Southwest earlier this year, I believe. But you just have this little annulus of light that you see. And the center part is dark. Okay, so that's an annular eclipse, and it's a type of partial. And here's just a time sequence. I've been showing you time sequences of these. And, you know, the sky doesn't get as dark because you still have maybe 10% of the light, 5 to 10% of the light. It does get a little bit darker noticeably, but not dark like during a total eclipse. And what's kind of interesting, we'll learn when we get to lesson 6 due to tidal interaction between the Earth and the moon is getting farther away each year, just a little bit, like a centimeter each year, something like that. Maybe it's a couple centimeters. I can't remember exactly. It's a good number, actually, keep in mind, centimeter per year. It's the rate at which continents drift, the rate at which Mount Everest is rising, the rate at which your fingernails grow, and the rate at which the moon is moving away from the Earth. So it's a good catch-all number. Anyway, what that means is if you go forward in time, millions, billions of years, the moon will be farther away and angularly smaller and will never cover up the sun. In our distant future, there will no longer be total eclipses on Earth. And in the past, it was closer, which means it covered more of the sky, and every perfect alignment was a total eclipse, and you had no annulars. So we live at this unique time when you can have totals and annulars, depending upon timing. Let's see what's next. Oh yeah, and we'll hit this slide a couple times today. This is just showing all the total solar eclipses and all the annular solar eclipses over the past 20 years. Well, from 2020 through the end of 2022. Through the beginning of 2000 to the end of 2020. And looking at this, we've experienced all of these now, except I think this one, December 14th, 2020. We'll have one pass through lower South America, Chile, and Argentina. This one that happened last summer passed right over my telescopes, but I wasn't able to get there to see it. Though, as we talked about last time, many of you saw this one in August of 2017. And there's going to be another one that passes, I think, from Maine through Texas in a few years. I think it's 2024, if I recall. So if you missed this one, that's one to try to make an effort to see, because it's really worth it. Anyway, we'll hit this slide a few times. And of course, it doesn't show the lunar eclipses. Remember, lunar eclipses can be seen from anywhere on the dark side of the planet. So there's really not a great reason to plot paths. If you're in the nighttime sky, you can see it. It's always during a full moon. And you know, the full moon rises when the sun sets and sets when the sun rises, as we saw from the warm-up question. Anyway, one question about this map. Notice how the paths get really thick at the top and the bottom. What's going on there? What's the primary effect? Is that real, or is that something else?
The sun's hitting it at an angle, so it's like the light isn't as direct.
Yeah, so it's two effects. One is that since the light is coming in kind of on the top of the globe, it gets spread out a little bit, and that contributes to it a little bit. But there's a bigger reason why those paths are so thick up there.
Isn't it the map is like warped because it's technically a globe, and when you flatten it out, it looks dumb. That's why I hate.
That's right.
Iceland and Greenland look so big when they're actually not.
That's right. Iceland is tiny. Greenland, Russia, Canada, Alaska, they're not that big. It's a map distortion effect. Antarctica's, although they don't go all the way down, but in some maps they go all the way down. It occupies the entire bottom of the map. So map distortion is playing a role, and as I believe it was Saros said, the light is coming in at a glancing angle, so it gets spread out a little bit. So both of those are real effects there. Okay, come back to this. Let me see what's next. Yeah, a series of questions that will lead to the next topic. Next topic's eclipse seasons. And so the first question is, and the first two are easy, what is the phase of the moon during a solar eclipse? During a solar eclipse, the moon is, say again?
Oh, it's fall.
No.
It's new.
It's new. Let me put up the geometry for that one. So this is a solar eclipse. The moon is blocking the sun, so the moon is between the sun and the earth. So as we look at the moon from the earth, we're looking at the dark side. So it is a new moon during the eclipse, and both, before and after, it's in the new phase. And what is the phase of the moon during a lunar eclipse?
Full.
And this one can be a little misleading because it does move into the shadow and is darkened, but we still call it a full moon. It was a full moon before it moved into the shadow, after the shadow, and even in the shadow, it's still getting scattered light through the edges of Earth's atmosphere, as we talked about, illuminating the whole thing. So it's a full phase. So here's the tricky question. Why don't we have an eclipse every time we have a new or full moon?
Because the moon sits on an angle to the ecliptic?
The moon, or technically the moon's
Line of note.
its orbit. So let me use the dot cam to demonstrate this. Get my notes right. Yep, okay, so I'm gonna bring up the dot cam here. Let me see what's next. Yeah. And I'm gonna turn it around. Like that. And this and this. Okay. All right, I'll shut the door. So the 4-pound weight ball will be the sun. The table, I should stand over here so my head doesn't get cut off. The table is the sun-earth plane. And then this right here is my portable earth-moon plane. This is meant to be the earth. The ring here is the moon's orbit, so the moon is somewhere on this ring. The red line is something we'll learn about in a minute called the line of nodes. And so if the sun-earth plane, this right here, and the earth-moon plane were fully coincident, no angle between them, then yeah, every time the moon is here, which would be a new moon, we would have a solar eclipse. The shadow would cast on the Earth, and every time the moon was here, the Earth's shadow would cast on it, giving a lunar eclipse. But in reality, there is a tilt. I'll move it over here. I'll keep the Earth in the extension of the table, the Earth-Moon plane, so the Earth is supposed to be in that plane, but the Earth-Moon plane is tipped by about 5 degrees. 5 degrees is not much, it's just a little bit, but the Earth and the Moon are so small that it's enough that the Moon's shadow, when it's here, goes under the Earth, and the Earth's shadow goes under the Moon when the Moon is here. I'll exaggerate the tilt just to make it obvious. So at this point in the orbit, you cannot have an eclipse. But as we come around over here to this point in the orbit, the tilt is no longer pointed towards the sun. It's perpendicular. So hopefully you can see it in the webcam, but if the moon is here, they are collinear. The sun, the moon, and the moon's shadow will cast on the Earth, or if the moon is over here, it will be in Earth's shadow. So when we're in this part of the orbit, and again, you have to pretend my table is circular, because the orbit is almost perfectly circular. I just don't have the space in the room, so you have to give me that. But when we're at this part of the orbit, we can have eclipses, as long as the moon gets in the right position, which is not guaranteed, but this is the time of year when you can have it. We call it an eclipse season. Now, as I come over here, I'll come kind of behind it, we're now tilted again, and so can we have eclipses over here?
No.
No.
Good. See, I can't see you at the moment, so I was just waiting for audio confirmation that you're all still there, that I haven't had a blue screen and lost you all. And then when I'm here, we can again have eclipses. If the moon is here or here, we're all in a line. That's what this red line is. And we can have eclipses. So a second eclipse season, come back over here. No, back over here, yes. So we can have there are 2 eclipse seasons as it works its way around. Okay. Did that all work? I couldn't see the webcam as I was over there, but you saw what I was demonstrating? Okay, good. Let's write down a few notes. I'll have to go back to the table a couple times today. Let me switch back
one
to the...
question.
Yeah, go ahead.
Does the tilt of that plane process kind of like the Earth's axis does, or?
It does, and that will be our next and last topic.
Okay.
So I'll just wait on answering that question because we'll spend about 10, 15 minutes on it. Okay, so we saw that there are 2 eclipse seasons. And actually, I'll just show the slides here. I got someone noisy, so I'm going to mute them. Okay. We have, so this is what I just demonstrated, first with the slides, and then I'll put down some notes. So sometimes the tilt makes the shadows not cast on each other. That's most of the time. But during eclipse seasons, the tilt is actually into the screen and out of the screen. And so the sun, moon, earth, or sun, earth, moon are collinear, and you can have eclipses. And so you have a period of, I think it's like 38 days. It's in the ebook. I forget exactly, but I think it's around 38 days or so where you can have eclipses if everything gets into alignment. And then another 38 days or so on the other side of the orbit. And this is just what I demonstrated, moving around in 3 dimensions, but we'll also make use of the figures so I don't have to jump up to the table as much. So with the dot cam, I gotta flip this around again. Okay, so we have 2 eclipse seasons, and we call 2 eclipse seasons 1 eclipse year. And we'll learn in a second that the eclipse year is not the same as the calendar year. There's a slight difference, and it does have to do with this precession effect that one of you brought up. Now, let's write down the conditions to have an eclipse. And to do that, first, let's define a term. And the term is going to be line of nodes. And the line of nodes, technically, it's the intersection of the Sun-Earth plane and the Earth-Moon plane. So again, the table was the Sun-Earth plane, my board was the Earth-Moon plane, and they intersect, two planes tilted. If you imagine expanding them out so they pass through each other, they intersect, and that's what you see here. This red line, and it was also a red line on my prop. You can see there the red line. That is the line of nodes, and it's just the intersection of these planes. Here you see the intersection, and the line points to the sun. See, here you see the intersection, and the line does not point to the sun. So, bring this back up. So the conditions. First, the condition to have an eclipse season. So this is condition 1. You have an eclipse season when the line of nodes points to the sun. Again, you can see that here. Here the line of nodes is not pointing towards the sun. Here it is, over here it is. That means you're in an eclipse season. Doesn't mean you have an eclipse. To have an eclipse, you need one more thing. So this is the second condition, and both the first and the second have to be met. You have to be in an eclipse season, and the moon has to be on the line of nodes. Again, back to the diagram here. The line of nodes is pointing towards the sun, and if the moon is on the line of nodes, then we either on this side or this side, then we have an eclipse. If you're in an eclipse season but the moon is not in either of those positions, then you don't have an eclipse. So both of these conditions need to be met to have an eclipse. Now, the Earth is big. It casts a big shadow, so we have a little bit of wiggle room on the lunar eclipses. And the moon, is casting a shadow, and again, the Earth is big, so it's a big target. There are multiple places it can hit. And what this means is you don't have to have a perfect alignment. It doesn't have to be super precise. Since these are extended objects, since the Earth in particular is extended, we have some wiggle room. So I can just give you some facts. You're not responsible for these, but just to let you know how often these things occur. With the solars, you'll have anywhere from 2 to 5 in a calendar year. And the last time we had 5 in 1 year was 1935. Everything has to fit just right for that to occur. Lunars, you can sometimes have 0 lunars in a calendar year. In fact, I think we just went through a spell like that where we had hardly any lunars for some time. And the number of lunars plus the number of solars is always 7 or less in a calendar year. So that gives you an idea of how often these things occur. They're not infrequent. On any given year, you'll probably have a couple solars and maybe some lunars. Okay. Now, so kind of the last topic has to do with this precession question that we got. And it kind of goes to this figure being not completely truthful. If you look at this figure, it looks like you have 2 eclipse seasons, one over here, and then you start back over. There'd be 2 eclipse seasons every calendar year. And that's not actually the case. You have 2 eclipse seasons is 1 eclipse year, and the eclipse year is less than 1 calendar, which is also called a tropical year. Just some terminology. Tropical year is the technical term for our calendar year. Calendar year is 365 days. And the reason for this, well, what we call this anyway, is the regression of the line of nodes. Regression means backwards motion. So the line of nodes isn't fixed in space. In this diagram that we've been looking at, it's fixed in space, always pointed in the same direction. We're moving it around, but it's not changing its angle. And that's not true. It's actually rotating slowly in the backwards direction. And this has everything to do with precession. Yeah, spelled that right once I fixed it. precession. So let's tie those concepts together, and I'll go back to the webcam for this. Now you remember with precession, we're talking about tops. In fact, I think this is one that I asked you to watch by video because we had run out of time. But the conditions to precess are if the object is not perfectly spherical and it's rotating, and there's a force on it, it precesses. And before we talked about the precession of the Earth. So here's Earth, its axis is tilted in space, but we said very slowly with time this axis changes. It's because Earth is not perfectly spherical, it's a little bit chunky around the middle, and it's spinning, and since it's not perfectly spherical, it will very slowly change its orientation angle over 26,000 years to do a full cycle. So it's spinning quickly, once a day, it's orbiting once a year, and then over 26,000 years, it goes through one of these rotations. That's precession of the Earth, but you also have precession of the Earth-Moon system. So again, here's the Earth, the Moon is somewhere on the circle, and we can view it as a single object. Think of the Earth as a mostly spherical mass, but then you have a lump on the side. It's not physically connected, but imagine like a steel pipe running up from the Earth and holding the Moon. So it's like a single object. There's no pipe that does that, gravity does it, but you can think of it as a single object, and when you do so, it's clearly not spherical. It's like a sphere with a big heavy bump on its side. And you can think of it as spinning. Really the Moon's orbiting, but you can think of this as a unit, the Earth-Moon system, as a non-spherical spinning object, and there's a force on it, the force of gravity to the sun. So this whole system will act like a top. It has a rotation axis, and this rotation axis will precess as well. And regression means it goes backwards. So most things are orbiting counterclockwise, but this will spin in the clockwise direction. So let's start here in an eclipse season, maybe during an eclipse, but at least in an eclipse season. As it goes around, I have to slowly precess it in the clockwise direction. So the Moon's going around like this, but it is precessing as it goes, and that means the line of nodes will point to the sun early. If it didn't precess, it would point here 6 months later. But since it was precessing, this red line points to the sun a little bit early, so we've entered our eclipse season a little bit early. We keep coming around here, I'm precessing as I go, and we hit it early. The red line is pointing to the sun early. Now I greatly exaggerate. It's only 19 days early, so instead of here, it's kind of like here, but I exaggerate so you can see the effect effectively. Okay, so the Earth-Moon system is behaving as a top. Hopefully the 3D to visualize it in 3D and moving, hopefully that helps. These still diagrams are not very useful for that. Come back here to the dot cam. So it's 19 days earlier each year. So let's write some numbers down. The tropical year we know is 365 days. That's the calendar year. Technically 365 and a quarter. Actually a little bit less than a quarter, but about a quarter, and hence our leap years. And if we subtract 19 days off from this, then we're at 346 days, and this is our eclipse year. So a little bit shorter. Now in the homework, one of the questions is how many eclipse seasons in 9 tropical years? And this isn't like a deep fundamental fact of nature. What it is just an exercise in knowing the definitions and unit conversion. I would solve it with the bracket notation. I'm giving you a hint on the homework right now. But if I had asked you how many eclipse seasons in 9 eclipse years, what's the answer? Should be obvious.
18.
18.
18.
But the tropical year is a little bit longer, so there's a possibility that we could squeeze in another eclipse season or 2 or 3 or something like that. So view it as unit conversion. Start with what you know, 9 tropical years. Convert from tropical years to days. In one tropical year, we have 365 days. Convert from days to eclipse years. In 346 days, we have 1 eclipse year. And then for each eclipse year, you have 2 eclipse seasons. So if you treat it as unit conversion, you'll find out how many eclipse seasons are in 9 tropical years, and that will help you with that particular one. Okay. Questions about that? And if not, the last topic will be the Saros cycle, the pattern of eclipses repeating. So let me move those paper down there. And get a new
Sorry, but if you can go through the 19 days earlier really fast again, I quite kind of.
Yeah, so it's 19 days earlier because this figure is not actually true. It's rotating. So imagine an axis pointing out kind of along here, and this whole plane is it's spinning around the axis, but the axis is also changing. So as I demonstrated with the demo and the dot cam, and I'll do one more of those, and so you'll see it again in just a minute. The line of nodes points back. Now here it's pointing at the sun. And as we go around, by the time I get back to here, since this plane has rotated, the line of nodes points to the sun 19 days early. And that means we've done the eclipse year 19 days early. We're in an eclipse season 19 days earlier than we would have been last year at this point in the orbit.
Oh, it makes sense now. Appreciate it.
Okay, good. Okay, so the last topic is Saros cycle. And this is something that was realized in, let me see what's next. Yeah, realized in ancient, let me put the dot cam up. I was writing. In ancient times. In fact, there's evidence of this before written history. They've built it into some archaeological sites. So this was known forever. And that's the pattern of eclipses repeats. And they figured it out from the lunar eclipses in particular. Because if you think about the solar eclipses, back a long time ago, you couldn't travel the world. There's no communication from place to place over great distances. All you knew is what happened at your location. And solar eclipses, the totals, they hit your location really infrequently. You miss most totals that are happening out there on the globe. And the partials, you don't see those most of the time. It's like a cloud passing overhead. A partial could be going on and you don't realize it. So they figured this pattern out from the lunars, because anyone on the dark side of the planet can see the lunar eclipses, and they started to keep track of them. And even though they're missing half of them, it only took them a couple generations to figure out, oh yeah, there's a pattern here. Eclipses repeat. The lunars repeat, and the solars repeat. So I'll start by writing out the equation that gives the condition for repeating, and then I'll I'll turn the camera around and try to explain it with the props. So the condition is n, where n is some integer, 1, 2, 3, 4, times 1 eclipse year is equal to m, some other integer, times the lunar month. So, n and m are integers. I'll try again, integers. 1, 2, 3, etc. Okay, so we got to find the values of n and m for which this works, but I also have to explain why this is the equation. So turning around one last time. Flip, flip. Okay, so suppose we are in an eclipse season, like right here. And let's suppose an eclipse is going on. It could be a solar or a lunar. It doesn't matter, but it's at one of these positions. Let's say lunar, since those are the ones that we're seeing most readily. And the moon is orbiting counterclockwise, so like this, as I go around. And if I have an integer number of lunar months in one eclipse year, then at the end of the eclipse year, I'll be exactly back where I started. And so whatever happened in that year will happen again. This is not the case, but let's first consider the case of n of 1. So as I'm going around, there's 1 lunar month, 2 lunar months, 3 lunar months, 4 lunar months, so forth and so on. I get over here, it's the beginning of a new eclipse year. And if there was no precession, it would be here, but because of the precession, the regression line notes it happens here, 140 some days. And if the moon were back in the exact same position, then whatever eclipses happened during that cycle will happen again. We're back at the exact same starting point. So if I do another eclipse year, end up over here, then whatever pattern of eclipses happened would happen again. That's not the case though. After one eclipse year, the moon does not end up back where it started. It's maybe over here. And so you can ask, well, what about 2 eclipse years? After 2 eclipse years, where's the moon? So after 2 eclipse years, I'm here because the regression line of nodes, it's over here. If the moon landed here, then whatever pattern of eclipses happened in those 2 eclipse years would repeat every 2 eclipse years, because we're starting in the exact same configuration. But it's not the case. The moon's over here. So what about 3 eclipse years? No. 4? No. 5? No. And you can keep trying. Eventually, some number will work, at least pretty close to work. And there's nothing deep and meaningful about it. It's just with an infinite number of numbers, eventually one of them is going to give you an acceptable answer. And that number happens to be 19. So when n is 19, we've gone through 19 eclipse years. That means we've had, well, it turns out that after 19 eclipse years, we have very close, not exactly, but very close to an integer number of lunar months. It's about 223, not that it matters. It's not exact, and that means the pattern will change slowly with time. But basically, every 19 eclipse years, we have 223 lunar months, and the pattern of eclipses that happens during those 19 eclipse years repeats over and over again. And I see it's 2:08. I'm just going to go maybe 3 or 4 minutes over today, just so we can get to the end of lesson 1. We're really close. You follow so far? There's a pattern and it will repeat because you're back at the exact same starting point as you were 19 eclipse years ago. The moon is in the same position.
Professor, I have a question.
Yeah, go ahead.
So in the textbook, it said every 18 years and 11.3 days. Is that like the same? Is it just like different numbers, but like the same? Like
That's my very next point. So good, thank you. 19 eclipse years. We know the eclipse year is not the same as the tropical year, the calendar year. If we convert it to tropical years, to calendar years, it's 18 tropical years and 11 and 1/3 days. That's what it converts to. So that means on our calendar year, it will repeat every 18 years, 11 and 1/3 days. Now, because of that 1/3 day, so it's repeating in time, every eclipse repeats on this time scale. Does it repeat at the same geographic location? And think about that 1/3 day. That gives you the answer.
No, it doesn't. No, it's
Because in 1/3 of a day, Earth spins 1/3 the way around. So let's go back to this diagram here. This covers 20 years, which is longer than 18. So let's find the first one and see if we can find its counterpart, 18 years, 11 and 1/3 days later. So the earliest one on this plot would be June 21st, 2001. We add 18 years, we're looking at 2019. We add 11 days, that would be 21 plus 11, so 32, June 32nd, which does, 30 days in June, so it's July 2nd, 2019. If you look over here, 1/3 of the Earth away, 120 degrees over towards the west, there it is. And in another 18 years, 11 1/3 days, there'll be another track right here. Then another, it's back to the same geographic location. Approximately, it's not perfect, but pretty close. So it repeats every Saros cycle, repeats in time every Saros cycle. It repeats in geographic location every 3 Saros cycles, 3 with 3 fingers, yeah. And just to avoid confusion, sometimes on the internet, in the literature, they'll refer to 3 Saros cycles, which is 54 years, as a Saros cycle. In this course and in the textbook, we refer to 18 years as a Saros cycle, and then 3 Saros cycles we call 3 Saros cycles. Sometimes it's called a Saros interval, but by Saros cycle, we'll talk about just the one of these cycles. A few final things about this plot here that can help with the final question in the homework. Notice the thickness, like from here to here, the path got thicker. And we said as you go up to the top or the bottom, the path gets thicker, but that's map projection and glancing angle of the shadow on the earth. But going to the left, none of that matters. So the fact that the path is thicker the next time means what about the moon? Closer or farther? It's closer, yep. Since it's closer, it casts a thicker shadow. And it can get closer still, and it can get farther away. So as you go from Saros cycle to Saros cycle, yes, solar eclipses repeat, but totals can become annulars, and annulars can become totals. It's just the fact that the solar repeats, but the type of solar can change. And the other thing you have to keep in mind, because this diagram's misleading, it's only plotting the solars. But again, this applies to the lunars. The geometry is the same. It's all about, okay, I started here, and how many cycles, how many eclipse years do I have to go around before I'm back in the same position? Whether it's on this side with the solars or this side with the lunars. So the lunar eclipses repeat. They have their own similar pattern. And again, this is the one that, everyone on the dark side can see lunars. So this is how they actually figured out the Saros cycle, using the lunars. Okay, I think that brings us to the end of lesson 1. I didn't get into the psychological effect about why the moon is bigger on the horizon. It looks bigger on the horizon and smaller higher in the sky. If I get to that in the second class, I'll put that on the internet. Otherwise, I might do a short little recording and post that for you offline. The last thing I want to mention is that's it for lesson 1. And you can complete homework 1, and we'll move on to lesson 2. We normally start with the whole day lecture on archaeoastronomy, and I show you a program that I wrote when I was your age, a 3D simulation of Stonehenge, where you can actually see all the astronomical alignments, solar and lunar. You can basically insert yourself into this simulation and investigate it all. Since we lost a class on Monday, I'm going to assign that by video, a video of me in front of a classroom that was taped previously, because we are required to make up the missed class. And so that's how I'm going to do it. So it's actually already there. If you go to the YouTube site, that full class on Stonehenge archaeoastronomy is there. Go ahead and give that a watch before we meet again on Friday. And then we'll jump into the future and pick up with Greek models of the universe. Okay, I'll stop. And if there are no questions, I'll see you Friday. Thanks a lot.
Can you go back to the notes really quickly?
Yes.
Sorry.
Yep, there you go.
Can you go over the regression and precession as to why the eclipse year is shorter than the tropical year?
Yeah, so if we go all the way back to precession, we talked about tops. Let me bring up a relevant slide, and I'll put that back up 1 second. Let me move it so you can see both. almost. Okay, so back to the concept of precession, which we didn't actually cover live. You watched it by video. Oops, I went too far. There. So precession is this thing that tops do. They spin on their axis, just like Earth spins on its axis, but the axis changes its angle. It's the same angle, the same tilt from straight up, but the orientation of the axis changes. And you've probably noticed this if you've played with tops. And the condition for this to occur is that your rotating body cannot be a perfect sphere, and there has to be some force pulling on it. And the Earth meets that criteria. So it precesses, though since Earth is so close to spherical, it precesses very, very slowly, once every 26,000 years. Regression in the line of nodes can be understood in the same way. So I'm going to jump ahead to that plot. So you can think of the Earth-Moon system as a single body. Think of it as a rigid object where the moon is connected to the Earth. It's not physically connected, it's connected by gravity, but just think of the whole system as an object. They're both orbiting around a common center of mass. They're kind of like a single object. And as a single object, they are not symmetric, they're not spherical. The Earth is spherical, but if you tack the moon on the side, then it's not spherical. So you can think of the Earth-Moon system as a non-spherical, aspherical object. You can think of it as spinning, the moon orbiting the Earth. It's like the whole system is spinning. So that system itself should precess. If you imagine a rotation axis coming perpendicular out of this plane, that axis will do this. And what that means is the line of nodes will change its orientation. It's not depicted here. Here they're depicting no precession, no regression of the line of nodes. But because the system will precess, the line of nodes will regress, and it will, because of that, point to the sun earlier. If it's pointing to the sun here, it would then point to the sun at this point in the orbit. And then coming around, it points to the sun at this point in the orbit, early, 19 days early.
Does it precess clockwise or counterclockwise?
No, clockwise. It's opposite, and that's what regression means. And whether the precession is clockwise or counterclockwise has to do with how the force is oriented. Like most tops, if we go all the way back to the top scenario, like a child's toy top, here you see the precession and the rotation are in the same direction. The force is pulling down. The force is more sideways. Precession occurs in the opposite direction as rotation. And that's true both with the Earth and with the Earth-Moon system. So when it's opposite, clockwise, as viewed from the top down, we call that regression, backwards motion. Other questions?
I had kind of a weird question.
Good, those are the best.
Are we
Now the pressure's high though.
are we considered adults when we turn 18 because we've experienced a Saros cycle?
That is interesting. That is interesting that the Saros cycle is 18 years. It was known by ancient cultures going all the way back. As you'll see it but when you watch that video lecture on Stonehenge, if that, turning an adult is kind of a arbitrary number in society today. What makes an 18-year-old an adult and a 17-year-old not an adult? What is the origin of that? Could it possibly be traced all the way back to the Saros cycle and the ceremonies they likely had when a Saros cycle passed? Perhaps. I don't know. That is a really interesting hypothesis. Never heard it before. Perhaps.
Is there a fixed ending and beginning for a Saros cycle? Like there is like a year?
No, it's constantly repeating. They do assign an arbitrary date for, okay, we're now in cycle 2073. And then 18 years later, okay, we're in cycle 2074. So there is an arbitrary start, but it's arbitrary. It's just a continuously repeating loop. And I should say, and I did briefly mention, the pattern does change gradually with time because it's not exactly 223. It's like 223.003 or something. It's really close. And so the pattern lasts for a long period of time. But over longer periods of time, the pattern will gradually change because those numbers are not a perfect match.
Earlier, you were speaking. You're using the graph about the different directions of eclipses, and you showed how the one to the left 18 years later was larger than the one to the right, and you're speaking about how it's due to the moon being closer. Was that closer to the sun or closer to the earth?
Okay, so I think we have a couple things like this right here.
No, the one back a few
Oh,
slides.
yeah,
where you had
okay.
the
Yep, I
earth
know
that
what
was
you mean.
distorted.
The moon, yeah, so how the path got, I'll make this full size now, how the path got thicker from here to here.
Yeah,
That's
you said it was.
because the moon is, it's one solar eclipse, and here we have another solar eclipse. When we had that second solar eclipse, the moon happened to be closer to the Earth.
That's where I'm confused, because in my head I'm seeing it as like, if it's closer to the earth, wouldn't that make the shadow smaller? As with the moon being closer to the sun, I feel like the angle of shadow would be larger.
So the Earth and the moon are so close together compared to the distance of the sun that we don't, and two things, we don't really have to think about the varying distance of the sun, and also the Earth-Moon system is almost always the same distance from the sun. Almost perfect circle, the Earth's orbit around the sun. So it really is about the moon. I can show two slides. One is, let me go back to the beginning here. Where was it? There we go. So yeah, just to back up and clarify what I bumbled through there. The Earth's orbit's almost perfectly circular, and that's really the Earth-Moon center of mass is moving around the sun almost always at the same distance. But the moon's orbit around the Earth is not perfectly circular, or close to it. It's a little bit oblong. So this is the bigger effect. If the moon is closer to the Earth, like over here, it will appear bigger. If it's farther from the Earth, it will appear smaller. And when it's closer, it casts, got it right here. Nope, almost. Yeah, here we go. When it's closer, its path of totality comes down and touches the Earth. And the closer it is, the bigger the spot is. So the wider the path is. But when it's far from Earth, here, the path of totality doesn't even touch the sun. And so it's, in this case, we're in annular territory. But you can imagine in between where it's still touching, but barely touching, that's a narrow path.
Okay, thank you. That really helps. Because I was thinking of it as like, if I put my hand closer to a light, the shadow of my hand is going to be bigger. But
yeah,
that explains it. Thank you.
Yeah, but if the light were a mile away, doing this versus this won't make, the sun effect won't be the big difference.
Yes, thank you. That helps a lot.
Can you go back over the Saros cycle, the 1 versus 3? I kind of missed like the geographic location.
Yep. So we can see it on this plot here. We know it repeats in time every Saros cycle, which is 19 eclipse years. And if you convert that to tropical years, it's 18 tropical years, calendar years, 11 1/3 days. And so that third day means that before the next one occurs, we have an extra 8 hours. And during those 8 hours, the Earth rotates 1/3 the way around. So when it repeats after one Saros cycle, it will land over here, not in the same geographic location. At the same time, but it doesn't hit the same geographic location. But since it's a third, that means 3/3 is 1. And so after one Saros cycle, it hits here. The next Saros cycle, it's not plotted here, but it will hit here 18 years later. And then another 18 years, it will land back at the same geographic location. So 3 Saros cycles, 3 repetitions in time. You also have a repetition in geographic location.
Thank you.
And of course, as you go from cycle to cycle, totals can become annulars, annulars can become totals, narrow paths can become thick ones, and vice versa. Other questions?
Oh, for office hours, is the Zoom link the same as for this class, or is it a different Zoom link?
It's a different Zoom link, and it's in the syllabus, and those have already been scheduled, so I'll stick to that other Zoom link.
All right, thank you.
Anything else? Okay, next class begins at 2:40, and I'll just pause and reset. Just to wrap up with the e-poll, which I think I've kind of given away most of the answer now, but we'll give you a shot at it, and then I'll answer any remaining questions. So the question is about the discovery of this pattern. It was discovered before even written history. We find evidence of this in the archaeological record. There are many archaeoastronomical sites out there. But anyway, did they figure this out by watching total solar eclipses, partial solar eclipses, total lunar eclipses, partial lunar eclipses? Pick 2 is how this works. So given the number of people who are still here, about 50 of you, I'll give you just another 15, 20 seconds to put an answer in. Expecting to get maybe about half response. Okay, since we're running late, I'm gonna just jump to it. And let's see. The lowest answer would be 1-1, the highest, 1-2. The highest answer would be 3-4. That gets rid of that fun response there. And let's see if one of them stands out. 1 and 3. Now think about the total solars. You didn't get the right one. I'm going to give you another chance at this. Total solars in ancient times, you couldn't travel far. There was no distant communication. A total solar eclipse hits such a small part of the Earth that you're going to miss almost every one of them. And that makes it really difficult to figure out the cycle. You're only going to figure out the cycle if you notice a good fraction of them. And then you have to wait a couple cycles, a couple generations, good record keeping. So the question is, which 2 of these are the most noticeable? I'll reset and let you do it again. Okay, let's see how we're doing. I still got the one answer there. Yeah, real close between 2-4 and 3-4. The answer is 3-4. The reason it's not the partial solars, although that hits a big chunk of the Earth, right? The total solars, it's a small spot. The partial solars, it's a big spot. But are partial solars easy to see? No, you've probably been outside for many partial solars and didn't even realize it. It gets a smidgen dimmer, but you just think it's a cloud passing overhead and not even realize it. But the lunars, whether it's a partial or a total, can be seen by everyone on the backside of the planet. So they're the ones that allowed us to figure out the pattern even back in ancient times.